This is chapter 12, section 2 notes. This is all about Newton's first and second laws of motion. If you haven't watched the worm video, then pause this and watch that first. It's a good overview of all three of Newton's laws of motion. Okay, so if you watch that video, they kind of laid out all three laws, but today we're going to focus especially on Newton's first and second law of motion. We've got to kind of back up in history, and these three guys, Aristotle, Galileo, and Newton, made some of the greatest advancements in physics, and we still talk about what they've done. Newton specifically, Newton almost made the most boneheaded decision ever. He worked on this book Principia, and this book Principia, he started in like the mid 1600s. And if you had a copy of that book today, it would be worth in the neighborhood of $350,000 because it's a really sought after book, and it's still looked at as the most important book for physics and mathematics. It's Principia Mathematica was the full title of the book. But the boneheaded decision he made was he almost never published it. So he wrote this book in the mid 1600s and then did not publish it till like 1687, and he almost never did. And that's where we got these three laws of motion that we're going to be talking about in this chapter. So kind of crazy. Not all of Aristotle's and Galileo's contributions were always accurate, but they did definitely make some good contributions to physics. So let's jump into the laws. All right, so Newton's first law of motion. This is known as the inertia law. And inertia basically says an object at rest will stay at rest, and an object in motion will stay at motion, unless acted upon by another force. Okay, so if you have a book sitting on the desk, it's going to continue to sit on the desk, and it's not going to move unless someone comes by and pushes it. Okay. An object that's in motion is going to continue to stay in motion unless acted upon by another force. So this is also known as the seatbelt law, right? This is why we have seatbelts in cars, because if a car comes to a stop, you're not necessarily going to come to a stop unless you have something stopping you. So great examples of inertia are seatbelts, or you're in the cafeteria and you have an orange on your tray, and you come to a stop and all of a sudden the orange flies off because that orange didn't get the message. It's an object in motion and nothing was there to stop it. So there's lots of examples. We could come up with others, like falling off your bike if you hit the brakes too hard. I'm sure you could come up with some creative ones of your own. But for an object to move, unbalanced forces have to act on it. And I know we said an object in motion stays in motion unless acted upon by another force. So some forces that could act on objects in motion: friction, air resistance, hitting something, like flying into a wall. Okay, all of these things are other forces that can cause that motion to start, to stop. I'll give you a second to read this joke. So, inertia man is being an object at rest, and he stayed at rest. Okay, I know. I have to put in the bad jokes. All right, so Newton's second law of motion. You may need to pause here to write all of this down, but I like to call Newton's law of motion the FMA law, or basically it says that the acceleration of an object is equal to the force acting on it divided by the object's mass. Another way we could look at it is force equals mass times acceleration. So there's a lot of ways we could look at it. And this is why we talked about force being measured in newtons, and a newton is equal to a kilogram times meters over a second squared, because what is force? It's mass, which is kilograms, and then acceleration, remember, is meters over second squared. So that's why 1 newton is equal to this. So write down this full equation and then also write down the triangle because you're going to need both. We're going to do some practice problems here in a little bit. Okay, so this is a really important picture, and I know we understand this stuff, but we don't always break it down. So acceleration of an object is always going to be in the same direction as in the net force. So basically, which direction is the object going, and that's the direction that the acceleration is going to be going. But sometimes we can have a net force act in a direction opposite the object's motion. Okay, so for instance, this person in the car, if the brakes were hit in the car, the seatbelt would be a net force acting in the opposite direction of the person in the car. Okay, and that's what actually slows you down. But this is what you need to know, is that acceleration depends directly on force and inversely on mass. So what that means is it's going to take more to accelerate something of a larger mass. If you're trying to push an empty cardboard box across the floor, it's going to take more force to accelerate it. If you're trying to push a cardboard box that's full of textbooks across the floor, obviously it's going to take a lot more force. So less force for the empty box and more for the larger box. And it's something that we kind of know, but we never break down the laws and talk about it. So this is Newton's second law of motion. It's force equals mass times acceleration. All right, if we're going to talk about mass, then we have to talk about weight. And we use these terms interchangeably on Earth because we just do. But you guys know, and you should know from last year, that mass and weight are different. So if you have to, definitely pause this to write down the formula. This is one of the things you'll have to calculate, but as you can see, it's really easy to do. We know that acceleration due to gravity is, I'm going to get my pen here, is 9.8 meters per second squared. I apologize if you thought this number was going away. It is not. So don't forget this number, especially if you ever plan on taking science in the future. So acceleration due to gravity is g. Okay, and that's 9.8 meters per second squared. And weight is just mass times that acceleration due to gravity. This is why if we traveled to the moon, our weight would be about 1/6 that of what it is here on Earth, because our weight on the, or I'm sorry, the gravity on the moon is about 1/6 that of Earth. So I know we don't talk about it a lot because everything on Earth has the same acceleration, but just know this formula. And there's our G. Okay. Here would be like a really easy practice problem that we could do. We could do 112 times 9.8. Let me erase all this ink on the slide. So there we go. There's our formula. And then that's how we would solve it. And then there is our answer. So pretty straightforward. That's why I didn't make you solve it. 112 times 9.8, and there you go. You get a kilogram times a meter per second squared. And remember, this kilogram times a meters per second squared is equal to newtons. So both of these units are the same. And you'll definitely need to know those units on your test. And you'll need to know that these two units are equal. Okay, so here's your first practice. We've done this before, so you should know what to do, but basically you're going to pause this video, you're going to try to solve the problem using this triangle, and then you're going to play it again and see if you were right. And I gave you space on your paper to do this. Okay, so if an automobile with a mass of 1,000 kilograms accelerates when the traffic light turns green, and then we've got net force. So start by picking out what you have. So we have mass, right? And mass is here. And you have force, 4,000 newtons. And force is here. Force is on the top. So we divide 4,000 by 1,000, and pretty easy. Here is the unit cancellation that we've talked about. If this unit cancellation confuses you, then just memorize the units, right? Force is measured in newtons, and we know that a newton is equal to a kilogram times meters per second squared. So you could see both. We know that mass is measured in grams or kilograms, and we know that acceleration is measured in meters per second squared. And what is the problem asking for? It's asking for acceleration. So we know that the unit needs to be meters per second squared, okay? Don't lose points because of units. All right, here's our next problem. Okay, go ahead and pause this, try it, and then play it again. All right, so the boy pushes forward a cart of groceries. We've got mass, and then the problem says, what is the acceleration? So we know that's going to be meters per second squared. And then we have force, and here is your answer. Okay, here is your next problem. All right, what is the upward acceleration of a helicopter with a mass of 5,000 kilograms if the force of 10,000 newtons acts on it in an upward direction? Okay, so pause it and then come back for the answer. All right, so acceleration equals force over mass, so 10,000 over 5,000. We've got 2 meters per second squared will be the helicopter's acceleration. All right, pause it, try it, and come back. So here we go. We've got mass of 12,000 kilograms. We've got acceleration, and then we need to know the force. So we know it's going to be measured in newtons. So here is your answer. Okay, so 1,200 kilograms times 3 meters per second squared, and then we get our newtons. All right, here's that same type of practice problem again. All right, so we've got 25 newtons. We've got acceleration, meters per second squared. And now we want to know the mass. So look back at that triangle and try to solve this. And here is your answer, 50 kilograms.